This revolutionary new observatory will locate threatening asteroids and millions of galaxies. This is the Rubin Observatory. And beginning next year, the Vera C. Rubin Observatory will use the world's largest digital camera to give us a whole new view of the universe. Dan Falk of Smithsonian Institute reports, the casual observer may envision the night sky as being static. When we look at Orion, for example, or the stars that make up the Big Dipper, our view is very similar to what our grandparents or even their grandparents would have seen, worsening light pollution aside, but this apparent lack of change is an illusion. When astronomers look at the sky more closely, countless transient phenomena come to light. Stars that change in brightness, known as variable stars, get brighter and dimmer. Supernovas burst into view and then gradually fade away, and thousands of objects too faint to see with the unaided eye, like asteroids, move steadily across the sky. Now, a new telescope designed specifically to track these changeable objects is set to give astronomers their clearest picture ever of the dynamic processes at work in the cosmos. At the same time, the telescope is expected to yield new insights into the universe's unseen elements, such as dark matter and dark energy. The Vera C. Rubin Observatory, nearing completion on the mountaintop in northern Chile, features a telescope that's enormous but also incredibly agile. The telescope, with a primary mirror 28 feet across and 3.2 gigapixel camera, will sweep across the night sky night after night, requiring a mere 5 seconds to reposition itself after each 15-second exposure, thanks to its large field of view, encompassing an area equivalent of 40 full moons, and its ability to move swiftly. The telescope will scan the entire visible sky every 3 days. Over the course of its planned 10-year run, it will photograph everything visible from its latitude some 800 times, flagging anything that pops into view, disappears from view, or changes position during that time. Everything about it is big, says Robert Bloom, the observatory's director for operations. The telescope's weight means it has a lot of inertia, he explains, which means that once it's been moved, it settles down quickly into its new position. We routinely discuss saving fractions of a second in the overall process of moving, settling, and exposing, says Bloom. But it also has, but who is also an astronomer, of course, at the National Science Foundation National Optical Infrared Astronomy Research Lab in Arizona. He says because a fraction of a second in each element of the observing program over 10 years, it actually makes a big difference. At the heart of the telescope is the world's largest digital camera, which is about the size of a compact car and weighs around 6,600 pounds. The camera, together with the telescope's optics, will have enough resolving power to see an object the size of a golf ball 15 miles away, or equivalently an object the size of the White House on the moon. And built at the SLAC National Accelerator Laboratory in California, the camera was shipped to Chile on a Boeing 747 cargo jet this spring and arrived at the observatory May 16. The primary mirror was built at the University of Arizona's Mirror Lab in Tucson, and it was shipped to Chile and installed at the observatory 2019. The $1.9 billion facility is due to begin operation early next year. Recording images is just a first step. Every time a particular patch of sky is photographed, computer algorithms will automatically compare the view to what was seen when the same patch was previously imaged, flagging anything that's changed. Every night we'll see about 10 million things change in brightness or position, says Mario Jurek, an astronomer at University of Washington in Seattle. He said, out of those 10 million, you want to select a handful that may be worth following up. That process, Jurek explains, will be highly automated given that the camera will be recording more than 6 million gigabytes of data per year. Researchers are still developing the algorithms that will ultimately be used to sift through the enormous volumes of data. When the observatory starts in 2025, it'll be a gold rush to figure out what's the best algorithm to find the most interesting objects, says Jurek, so that'll be the super fun. The Rubin Observatory is expected to discover millions of previously unknown asteroids, small rocky bodies that have been circulating the sun for billions of years but have eluded detection because they reflect only a tiny amount of light. Jurek says the observatory will reveal some 5 million of these objects, ranging from marble size up to a few hundred miles across. Of particular interest would be objects like Umama, the interstellar asteroid, the cigar-shaped interstellar object that zipped through our solar system in 2017. If such an object were detected, alerts would be sent out to the astronomical community within hours so that other telescopes could zoom in on the object, says Jurek. And since the Rubin telescope will be able to detect these objects early, we'd have months rather than days or weeks to study it. With enough lead time, a space mission such as the European Space Agency's proposed Comet Interceptor, that means planet defense of course, could rendezvous with the object and examine it in more detail. Tracking asteroids is also vital to planetary defense. Today, astronomers are aware of only about 40% of the potentially hazardous asteroids, cross-flying objects that are large enough to cause continent-wide destruction if they were to impact our Earth, Jurek says. With the Rubin telescope, astronomers should be able to detect up to 80% of such objects. This is one discovery that all of us are hoping we won't make, he says, but the idea is if there is an object like that, we want to find it while it's maybe 40 to 50 years out, because that gives us enough time to figure out how we're going to deflect it. Further afield, Rubin will image millions of galaxies, flagging those where exploding stars known as supernovas are spotted. Supernovas are incredibly useful to astronomers who can use the exploding star physical properties to work out the distance to their host galaxies, and this in turn allows researchers to create 3D maps of the cosmos. Studying this distribution of galaxies can provide clues about the abundance and distribution of dark matter, an unknown substance that holds galaxies and galaxy clusters together, which along with gravity has shaped the evolution of the universe. Such 3D maps also allow scientists to study the effects of dark energy, a mysterious force that appears to be causing the universe not only to expand, but also to accelerate. Accurately mapping the distribution of galaxies will help pin down dark energy's characteristics, says Renee Chlozek, astronomer at University of Toronto, and a spokesperson for the Dark Energy Science Collaboration, a team that will be using data from Rubin to study the mysterious force. Rubin will also allow us to test different models of what dark energy could be, Chlozek says. Is it changing with time? Is it changing in space? With data from Rubin, we can actually put these ideas to the test, which is really exciting. The observatory had originally been referred to as the Large Synoptic Survey Telescope, but it was renamed in 2019 in honor of Vera Rubin, an American astronomer who made pioneering measurements of galactic rotation speeds in the 1960s and 70s, providing the strongest evidence for the existence of dark matter. The decision to name the observatory after Rubin is a real nod to her contribution in the field, which some would say has historically been undervalued, says Chlozek. This is on Collective Spark by Dan Falk from the Smithsonian. Please leave your comments and thank you for your support. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.